Okay, today I'm going to be going over how to solve bridge problem number 4 for the Principles Engineering class at Bishop Alemany High School. Okay, so I've got all my points labeled A, B, C, D, E, and F. Notice that here the pin and the roller are in different places than we're used to. That's basically the only difference with this problem compared to problems we've done before, but that is a key difference. So we're going to be solving for the reactionary forces at the pin. There's got to be one horizontal one and one vertical one. So we will call this RDX and RDY, maybe. And we'll be solving for the reaction force at this roller, which has got to be horizontal, and which we will call RAX. Okay, so in order to solve for this, we need to set up our torque table, like we always do. We're going to be looking at clockwise and counterclockwise torques. We've got 3 external forces happening on this thing, and then obviously the reaction down here. These will not be causing any torque because they're happening to the pin, which is our rotation point. So we'll deal with this force first. The question is, how much torque is this force causing? And the answer is it's actually causing none because it's in line with the pin, right? So the perpendicular distance to this force is a vertical distance, and there is no vertical distance from here. So this force is not causing a torque. So we can come down to this force. This force is causing a torque. It would cause this bridge to rotate up that way, which is counterclockwise. And the perpendicular distance to 600 is this distance here, which is 4. So this is a counterclockwise torque that is 600 times 4. Okay, now we've got this force, which is causing a torque. It would cause the bridge to rotate that way, which is clockwise. So that's a clockwise torque, 1200. And the distance, the perpendicular distance from this vertical force, is the horizontal distance, and the horizontal distance is 4. All right, and then finally we've got the torque caused by this thing. It's a horizontal force, so we're looking at the perpendicular distance, which does exist here. So it is causing a torque. It would cause the bridge to rotate this way, which is counterclockwise. The way I currently have it drawn. But that also makes sense because obviously 1200 times 4 is more than 600 times 4, so we need an extra counterclockwise torque here, so that will be RAX, and the distance is 4. Because again, the vertical distance here is 4. Okay, we need these sides to both equal the same things. We've got 4800 on the right, has to equal 2400 plus whatever RAX times 4 is, so 4 RAX. It should be incredibly apparent what RAX is, it's just 600. So I will write that over here. So this is 600. I need it to rotate this way in order for it to be counterclockwise, so it is pointing in the correct direction already. I don't have to change that direction. Get rid of some of this stuff. So this is a 600 right there. And now I am done with all of this. Clean up a little bit. Okay. Now that I've got this unknown force, I need to find these unknown forces using translational equilibrium. So we need all the rights and lefts to equal each other first off. So we've got 600 right, 600 right, and 600 right. That's a total of 1800 to the right, which means that this force RDX here, which I currently have drawn the wrong way, must be going left first off, and it must be 1800 in order to cancel out those forces. This force here has to cancel a downward 1200, which means it's obviously going upwards, so let's get rid of that. and it is going up, and that upward force is 1200. All right, so now that we've got all those forces, we can start solving for different joints. And I'm going to pick joints that have the least going on. I guess I could start at this roller down here. I'm not going to redraw this out because it's fairly straightforward without needing to do so. We've got 600 going to the right, which means to counteract that here at the joint, we need a 600 going to the left. If it's going to the left, that's pushing into the joint, which makes it a compression of 600. All right, that joint is now actually done because this is just 0 because there's no vertical forces here, so that must be 0. Okay, coming over to here because this is another really simple area. Obviously this is 600 going to the right, which means there needs to be a 600 going to the left. Going to the left would be pulling on the joint, which makes this a 600 tension. Straightforward. And again, this must be 0. So I didn't need to draw out C. It was all pretty straightforward. Okay, I can immediately say that this is 0. There's absolutely no way that there's any vertical forces for this thing to cancel, so I'm just going to go ahead and call that 0 right away, just to kind of simplify things. Which, now if I come over to F, which might seem like a strange place to go because look at all these bars, but this bar is 0, and then notice that there's only a horizontal force that needs to be canceled. There's no vertical force that needs to be canceled, which means that this bar must be 0 because it has a vertical component, and nothing would be able to cancel that vertical component if this was anything other than 0. So this bar must be 0. And this bar, therefore, must be 600. It's pulling to the left to counteract the rightward force, so it is a tension. Which then lets us solve this, is a 600 tension as well. Because if we look at joint E, we've got 600 pulling to the right, which means we need 600 pulling to the left, which is what this bar is. All right, so we're already down to our last member, this diagonal one right here. So this was actually a pretty quick one, it seems like. We're gonna have to actually probably draw out this one here though, because there's a lot of stuff going on at this joint up here. So let's draw it out. We'll draw it out on the side over here. So this is gonna be joint A. As soon as it lets me draw it. Okay, so this is joint A. We've got 1200 going upward. And we've got 1800 going leftward. These are known forces. We've got a 600 tension right here. Look at that in parentheses. This is a 600 tension, which means it is definitely pulling to the right with 600. All right, we've got a 0 downward, so I'm not going to bother drawing it. And we have an unknown diagonal. And this diagonal, because this is a 4 by 4 triangle, this diagonal is a 45-degree angle. All right, so let's combine this 600 going to the right and this 1800 going to the left. So let me go ahead and get rid of it. So we've got a combination of 600 right and 1800 left is 1200 left. Looks like that. So we've got 1200 up and 1200 left, which means we need 1200 down right here and 1200 right here, which makes the hypotenuse here, if I were to redraw it, this hypotenuse must be 1200 root 2. So that's exactly what this is, 1200 times the square root of 2, and it is pulling down into the right, which makes it a tension. Okay, so there's really only one joint that we had to redraw and try to solve for, but that is it. That's the whole problem. So this problem just it seemed to me like there was a lot of struggling with this problem. So make sure that you review this video, you understand what I did, how I simplified this problem. I didn't necessarily expect this problem to give people so much trouble after all the ones that we've done. Maybe it was switching the roller and the pin to opposite sides, but honestly, this is the exact, if you had just if you just rotate your head a little bit, this is no different from other problems with the pin on the left and the roller on the right, except now this, you can think of this as the ground if it makes it easier for you. But you can have a bridge pinned in different areas as well. Let me try to scratch some of this out. Anyway, let me know if there are any questions about any of this. I'll see you all in the next video.